Hey everyone, this lesson is just some basics on logarithmic functions, not really common or natural logs just yet, but just the basics and comparing that with exponential form. So thanks for watching. Don't forget to like, comment, and subscribe. All right, logarithmic functions, as it turns out, was just another way for math people to write exponentials. And then, of course, we make you guys learn about it to make ourselves feel better about ourselves. Sorry about that, but that's the way life goes sometimes. It actually just means the exact same thing. It's just written a very different way, right? Now, this mean stuff means that it goes both ways. So you can start in exponential form and change it to a logarithm. You can start in logarithmic form and change it to an exponential. It depends on what's more convenient and what value is missing, which may help us to figure out, I guess, whatever unknown they give us. And notice the b value cannot be 0, because if your base is 0, it doesn't matter what your exponent is. You just get 0. And so it has to be greater than 0 as well, because your base value, if your base value is negative, then you can jump around with evens and odds kind of thing. We're not too worried about that. Formally, I'm looking at this y equals log base b of x stuff. That's how it would be said. Y equals log base b, and then sometimes that x will have parentheses around it like this. So it's base b of x, kind of like we would for a function, right? Yeah, that's good. So evaluate f of 64 for f of x equals log base 4 of x. Okay, well, let's rewrite the function here first. Now up here it's f of 64, so we're going to replace x with 64. And we got to evaluate this stuff. So f of 64, some of you guys can put this directly into your calculator. Some of you don't, or you can't because we haven't shown it yet, but you can. Let's assume that we never knew that you could with the calculator stuff, right? Well, that f of 64 stuff is really just the corresponding y value for this. So it's log base 4 of 64. Again, that doesn't really help us, but if we change it to exponential form, hopefully it will. So I've got base 4 to the power of that y, and this equals what the log was of, and that's 64. So 4 to some power is 64. Now, if that was some decimal value, we would absolutely need a calculator. But we can look at multiples of base 4. 4, 16, 64. So we see from that y is 3. Let me show this differently, actually. 4 to the power of y is the same as 4 to the power of 3. And we've seen same base stuff before as well. And when the bases are the same, then we just equate the exponents. Y equals 3. And that would be our answer for this. But y really was f of 64. Yeah, that's just formal. In the homework, you just punch in 3 in the box and you'll be done. Write this logarithm in exponential form. No calculation at all on this one, right? So let's look at log form. So it's always log base b of x, and this would equal y or f of x. Okay. And then this changes into base b to the power of y, and then it equals that x. Now, again, it was from that first slide, right? So just changing these, right? The y value here is shown as 1/3. The base is 8. And this should equal the x value, which is 2. And we've changed that into exponential form. You could check that in your calculator as well. Okay, you've only got 3 numbers on this, which makes 6 different possible ways to write it, I think. So if you did something like 2 to the power of 1/3 equals 8, you could type that in the calculator just to make sure that it works, which it wouldn't. But 8 to the power of 1/3 does work. And we know from rational exponents, right, this is really just the cube root of 8 is 2, which is a true statement. Again, we're just changing this logarithm to exponential form. So let's look at the change there, right? All right, so the base here is 2, so I can replace the base in the exponential form is 2. The x is 1/4. Again, it doesn't matter what order you do these in either, as long as you know where they go. X is 2, I'm sorry, 1/4. So I'm going to replace the x in my exponential form with 1/4. And then the y value was that -2. So I'm just replacing the y with -2. And again, that's something you could plug into your calculator just to make sure it is true. And it is. We're good there. All right, we're going to change these exponentials to logarithmic form. So again, let's look at the change there. All right, so let's just find these values. The base here is 4. So I'm going to change the base to 4. The y value, the exponent, is the answer for the logarithm. So I'm going to replace the y with that exponent of 2. And then the x value is 16. So I'm going to replace that x value with 16. Logarithmic form. Bam. Done. All right, what about this one, right? The exponential equation in logarithmic form. Okay. It's just switched around, right? Now it's more of a y equals, x equals b to the power of y. And that should transform into log base b of x equals the exponent y. So our base in this one, right there, is 10. So I'll replace that with 10. The exponent is -2. That's the y value. So we'll replace that -2. And then the x value here is 0.01. There we go. We'll change that to 0.01. Now, I don't think they're trying to get to this yet, but that's a common log, which we'll talk about later. We usually solve logarithms by changing them back into exponential equations. Yeah, so this is just for solving for missing values. I want to say sometimes it's the base, sometimes it's that x, sometimes it's the exponent. You just never know, really. If it was the x, then it's not too bad, because then you have the base and the exponent. You just plug that into the calculator and be done. Yeah. But again, we got, well, this one would be the x value, right? So this log base b of x equals y. Now they're using b as the variable here, not as the base. So if we were to change this into exponential form, our base value is, well, it's the base, and it's to the power of y. And then it equals this x value, which in this case is the unknown that we're looking for. So that makes this one, I'd say it makes it pretty easy. We know the base is 6, which actually looks like a b. And then the y value here is -4. So it's really 6 to the power of -4 is b. Let's see. Oh, actually, that's the way they have it written in the key that I have. So looks like there's no need to evaluate that, no decimal, no need for the fraction on that. We'll just write it like that one. All right, this one we will solve, so we want the actual number, not the exponential form of the answer. So this is our base, right, and it's always the base to the power of y equals the x, which in this case is x, so that's not too bad. But the base I can replace with 8, and the y value is the 7 right there. So it's 8 to the power of 7, which is actually pretty big. I got x equals 2,097,000 152. All right, if we don't like using factoring, which sometimes is necessary, I don't remember seeing any quite like that on the homework, just like the examples we did. But we can change the base, we can use the change of base property to actually plug the logarithms into calculators that don't have the actual logarithmic form in the calculator. All right, change of base looks like this. So notice the C value on this one. All right, these C's, that means we get to change the base to whatever the heck we want it to be. And we'll look at this a little bit later. And there's a proof of this, but it's on, I guess I'll try to put on Canvas from YouTube. But it's the base value, the log base, the base value here is in the denominator now. And then the A value, which is the log of, is the numerator. Generally, we try to change these into natural logs or common logs, all right? So, and well, that's what allows us to put them into the calculator. If, again, this is only if we don't like the factoring. So with the factoring stuff, yeah, we'll do that on the next one, factoring, and then we'll show the calculator. So on this one, if I were to change this into exponential form, I'd have 4 to the power of x equals 1 over 16. Factoring, we would want to look at 16, we'll divide it by 4, and see how many times we can divide it by 4 until we get 1, right? Well, that's just 4 and 4. So I got 2 4s, right? So 1 over 16 is really 1 over 4 squared, which is 4 to the power of x. And 1 over 4 squared is really 4 to the power of negative 2, which equals 4 to the power of x. Now again, if our bases are the same, we're going to get rid of them and just compare the exponents. So this ends up being negative 2 equals x. Sometimes that'll be in an equation that you actually have to solve. But in this case, this is good. We found the value of x. That wasn't too long. I mean, 16 is not too bad of a number to deal with, especially with base 4. If it was base 2, it would be a little bit bigger. Let's say that we didn't want to do that. All right. Now this is, again, before we look at common or natural logs. But let's say that we wanted to change the base on this thing, okay, so that we could plug it into a calculator. The question really becomes, is it easier to find the log button, and it should just be log on the calculator. Sometimes it's its own button. Sometimes you're going to be looking for this button. Sorry, my cursor's not great. That's ln. That would be natural log, and sometimes it's its own button. Sometimes they're like the second button. You got to push the second button and then the log button to get the natural log. Whichever is easiest for you, all right? What this means is that we could have plugged it into the calculator as, well, which one do you guys want? All right, so let's do that. All right, so I got the natural log, and it would have been of x in this case, which was 1 over 16. And, you know, depending on your calculator, you have to do the 1 over 16 first. And we're going to divide it by the natural log. It's the same base, which we'll get into, of the base value, which is 4. Once you plug this into the calculator, it should spit out that negative 2 business. All right, solve this one. Now again, we'll do this both ways once again. It doesn't show that it equals y, but you can just say that it equals y. Just because that's, I guess, the form we're used to seeing, right? So this would be 5 to the power of y, just going to exponential form, equals 3,125. And 3,125, again, the factoring is going to be delicious on this one. 600 and, what is that, 625? Yeah, that's good. And that divides by 5 as well. 100 and, it seems like I did that wrong. All right, so 3,125 becomes 5 to the power 1, 2, 3, 4, 5, which equals 5 to the power of y, right? But we got the same base, so we're just going to compare the exponents. Y is 5. That wasn't too bad. I mean, dividing by 5 is not too bad. 7s kind of get a little sticky, but with a calculator it's not too bad. But if we're going to use a calculator, we may as well just use the change of base stuff. So that means we can go back up here. We did the natural log last time, so we'll use the common log. If you'd find your log button, we want the log of 3,125, and we'll divide it by the log of the base, which is 5. And when you punch that in, once again, you should get 5 out of that. So, I mean, if you wanted just to check, just to show that it doesn't matter that we change the base, you could do the natural log of 3,125 and divide it by the natural log of 5. It's not going to matter. You can get the same answer. All right, these are characteristics of logarithmic functions. Oh, that says lob. Sorry, that's a typo. That's a... Yeah, the G and B are close together, so I don't feel too bad. But it's log. Log base B of x. Where are the asymptotes if we were to look at those two purple lines? Yeah, now it's the vertical line, right? So we got that vertical line now, right here. So before, the horizontal lines were y equals, now this one would be x equals 0, right? That's our asymptote. X is 0. But notice the change in the domain and range on these, because you're going to be asked about the domain and range. The domain, it doesn't reach 0, but it will get extremely close to it, okay? Which means that 0 is not included, and then it's going to go all the way to the right to infinity, which again is not included. If we were to look at the range, how far down does this thing go? I mean, it's kind of shows that it's evening out there, but it's never going to actually even out, which means we can go as far down as we can to a negative infinity. And then how far up does this thing go? All the way to positive infinity. It's the same way for this one. It goes infinitely down and infinitely up. So the range is from negative infinity to positive infinity. Y equals log base 3 of x. That's pretty straightforward. However, it's kind of hard to graph with logs, which you can do, right, with the change of base stuff. I am not going to use the logarithm. What I'm going to do is change this into exponential form, so it's be 3 to the power of y equals x. Now this means that the x is going to change based on what y is for us. So when we make our table, x and y, we're actually choosing values of y instead of x. So we could do -1, 0, and 1, which is what we would usually do for linear type equations, right? So if y is -1, 3 to the power of -1 is 1/3. So that gives me that point, 1/3 -1. It's not perfect, but somewhere in that area. Then we got 3 to the power of 0, which is 1. So again, that gives us another point, 1, 0. And 3 to the power of 1 is 3. So we have these 3 points. There's 3, 1, which again would be enough. We should be able to tell just from what we know about exponential functions that this thing is going to get really close to the y-axis there, but never really touch it. And then it's just going to increase. It's going to go to the right really fast, but not really up very fast. And that, again, is because it's inverted. Yeah, so if we wanted to find the asymptote, the equation for it, right? Again, that red line is getting really close to the y-axis. So the equation for the y-axis would be x equals 0, and that's the equation for the asymptote, because it is a line. All right, graph this one. Again, I like to change this into exponential form and then make the table from there. So exponential form, the base of 2 to the power of y equals x plus 2 now. Now that x plus 2, we don't really want it there because we're going to be choosing values of y and then solving for x. And I don't want to really work with x after I've figured out what 2 to the power of y is. So I'm going to subtract 2 from both sides so that I just have x. So I've got 2 to the power of y minus 2, and that will be my x values on these. So now it's time for my t-table, whatever you want to call it. Let's try x is, I'm sorry, y. Yeah, let's choose the values of y, the exponent. Let's do y is 0. That's a nice easy one to start with. So I got 2 to the power of 0 and then minus 2, which is 1 minus 2, which is negative 1. So x is negative 1, y is 0. There's our x-intercept. Let's also try, what the heck, let's try y is negative 1. So that's 2 to the power of negative 1 minus 2, which is 1/2 minus 2, which is negative 1/2 or negative 1.5. So negative 1.5 and negative 1, about right there. Alright, next up, let's go on the positives. So we'll try 1. So that's 2 to the power of 1 minus 2, which is 2 minus 2, which is 0. So again, that's an ordered pair, 0, 1. There we go. Now with these 3 points, it is possible to graph this. It may be helpful to look at other values, like 2 maybe, which would be 4 minus 2, which is 2, 2, 2, and that definitely shows the pattern. We can show other ones as well, what the heck. But one of the questions I think we encountered on the homework is, again, where is the asymptote on this thing? Well, to do that, we're going to need more of these negative values, right? Because we did negative 1 and we did 0. But if we did y is, let's say, negative 2, then it'd be something like 1/4 minus 2, which would be negative 1 3/4, negative 1.75. So y is negative 2, negative 1.75. We can see right there that it's going to get really close to x is negative 2. Now again, that's just with the asymptote stuff. So there's our line, and let's draw the asymptote on this. And there we go. So the asymptote is that x equals negative 2. Again, not that it asked for it on this one, but and it may help to show that. Like, if you know where the asymptote is, draw it first so that you know where the line gets really close to. I've just seen it on tests where it's like, I got those points, so something like this. Sorry, you crossed the asymptote. I don't want to take the points away, but I kind of have to at that point. Be very careful with that, all right?